Hi, my name is Luca. So now I will talk about something which is a bit different. Will be the emulation of astrophysical model. That something that I was with Pierre Palu, which is just here from Lille. So in the interstellar medium community, numerical simulation are widely used in order to model the ISM and compare the theory with the observations. But the computation time is often prohibitive for inference procedure, and especially for Bayesian inference procedure, when you have to make a lot of calls to the simulations. And the usual solution that can be found in the literature are either to use interpolation method, for instance, the nearest posting grid or Sapien interpolation, which means that you will use the model which is time consuming to compute a grid, and then it will fill the whole of your grid by using one of those methods. And something which is already done today. And the second possibility is to use a regression-based approximation. So for instance, using machine learning stuff, for instance, the k-nearest neighbors, the random forest, or use of neural networks. But so in the literature, when we see this kind of solution, this is for models that are less complex, which means that they are faster and you are able to have more data in your grid at the beginning. And so this is more easy to have an emulation of the model. So in our case, we'll look at the modern PDR code, which is a code which will emulate the PDR regions at equilibrium. And in our version of the code, we have 4 inputs. I will say more about them later. And we obtain something which is higher than 5,000 spectral lines intensities at the end. So we can consider that this code is a function with 4 inputs and several thousand outputs. The execution time is about 6 hours, which is very long, and they may yield anomalies, something which is not physical, and sometimes the code cannot converge, or sometimes there are multi-stabilities, and those anomalies make that this is sometimes difficult to approach the code. But what is important is that the predictions are directly comparable with observations, and moreover, this is a representative example of ISM numerical simulation, so we use it as a template. And to say more about anomalies, there are something like this. So for instance, we have the one output of the code for several values of one of the parameters. And we have this point with a square, which is completely different from what we have. And for physical reason, we know that's something which wasn't supposed to happen in the code. And here in 2 dimensions, you have this point in yellow, which, like the previous one, wasn't supposed to be here. And when we will try to approach the code, we will try to get rid of this kind of points in order to have a result which is closer to what the physicist wanted at the beginning. So in a nutshell, the modern PDR code combines a lot of different physics, but to summarize, you have the physical conditions. So in our case, 4 physical parameters at the beginning, and you have 2 steps. The first one is that you will solve the cloud structural update profiles, and the second one, you will compute integrated values spatially, and at the end, so you obtain line integrated intensities, and so those things are encoded in the code, and you can just consider that this is a function which is deterministic, and this is what we want to approach. Most physically, this is a normalization of a PDR. You have the ionization front and the photodissociation front, and the region in gray are the ones that are modeled by the modern PDR code. In fact, here we have several parameters. So G0, which is the UV eliminations. You have some constants, either the thermal pressure or the densities. In our case, the model is at constant density. And so you also a parameter which is AV, and the 4th parameters is the angles of observation of the cloud. The function looks like this, and something which is multimodal, very nonlinear, and this is something which cannot be approximated using linear methods. So this is something which is really designed for the use of deep neural networks, and so this is why we'll go for this solution for the emulation. Something which is important is that for some reasons, Pierre needed to have a model which can be derivated, so we can derive the output with respect to the input. So we need our model to be fully differentiable, and this is important. And this is something that the neural networks are able to do. So to make it simple, we'll start from a very standard architecture of in deep learning, which is a multi-layer perceptron. So in this case, we have 2 inputs and 10 outputs, and each layer corresponds to a matrix multiplication containing weights that have to be learned by the model, and a nonlinear function, another matrix multiplication, another nonlinear function, etc., etc. This number of operations is called the number of layers, and the more deep is a network, the most able it is to approach a very nonlinear and complex function. But in our case, this is not very sufficient to have good results. So the first proposition is to create a polynomial expansion of inputs, which means that to help the networks create nonlinearities, we will create a lot of polynomials at the beginning. It will help the networks, but we have to ensure that this is fully differentiable in order to have an access to the derivatives. The second thing is to ignore anomalies. In our case, the anomalies are not the points that are strange, but the points that weren't supposed to be there. It's a bit different. And so the problem is that we cannot do this directly by hand, but to have an automatic method is complicated. So we'll do something which is in between. We'll first train the network with a robust loss function, for instance, the Cauchy function, in order to detect a badly reconstructed point. We'll address a list in decreasing order of starting from the points that are very badly approximated. And so we'll use physical knowledge in order to determine anomalies among them. And we'll use for that physical knowledge, can do it by hand. And in a few hours, we can have a data set when we have inspected the most problematic point in order to have a data set which is cleaned. And the third point is to train the network with, this time, non-robust loss function using a mask in order to ignore the point that has been considered as abnormal. Third proposition is to make output clustering, which means that we can split the line into clusters based on their similarity. The point is that we cannot train one network's bar line because it will be too time consuming. But if you want to train a network in order to approach all the lines, they will have some line that corresponds to very different behavior. So something which is more interesting is to train several networks, for instance, 4 networks that are dedicated to lines that are very similar in different clusters. And the method that we use to make this clustering is called the spectral clustering. So in our case, we won't have only one network, but we'll have 4 networks that are learning things in parallel. And the fourth proposition is to reuse intermediate computations. So in our case, we'll change the architecture in order to move the inputs to each layer to remember the previous inputs, because we know that for some reasons there are some outputs that are directly proportional to inputs, or some outputs that can be computed using other outputs. And if we are not doing this, the problem is that some part of the networks will have to approach the identity functions. And if the network is doing this, it will lose a lot of complexity to do things that are not necessary. And doing this are a lot of good properties. And in particular, we are able to have a network which is deeper with less parameters, so able to approach really nonlinear function with only a few minus parameters. And so once we have this this architecture which is evolved from multi-layer perceptron, we'll try to compare the result with interpolation method using 3 metrics. The first one is the accuracy. We'll use something which is called the error factor, which is a kind of symmetrized relative error. They are computing on unseen data. We'll have also the memory metrics, which is basically the size of the model. One important thing is that in the case of interpolation methods, the size of the model is the size of the whole grid, because the whole grid have to be loaded in memories to do interpolations. And the third one is the speed of the computation speed of the models computed on my laptop for a batch of 1,000 entries. And importantly, to be usable in inference, the emulation must satisfy some constraint on those metrics. And I can show you this. So the first figures show two metrics, the mean error factor in percent and the 99th percentile error in percent. Or why not the maximum error? That's why in the data set, especially in the unseen data, there remains anomalies that we wasn't able to detect because we are not supposed to do anything on the test set. So we prefer to use this metric, which is more robust. And in fact, to be usable in inference, our points are we need our points to be inside the green rectangle, and same for these figures, which corresponds to in abscess the memory size, and in the y-axis the speed on CPU. And what we can see is the interpolation methods are not inside this those green rectangle, but our method with some improvement are inside this this rectangle, which means that we can use them in interpolation, and Pierre will talk about this just after. For something which is important is that all these improvements that we add to neural network not mandatory. If you want to apply this for your own numerical simulation, you can start for the very standard architecture or just try one or two propositions. They are not completely not mandatory. It will depend from your use case. But what is important is that in our case, deep learning is very efficient to model this those simulation, especially with additional constraints. We imposed to have a lot of things, a different architecture. We wanted to have the reuse of intermediate results. The deep learning is very suited for this kind of constraints. Those emulators can be directly plugged in Bayesian inference. And something that I have seen in this work, but also in the previous one, was that AI will benefit a lot from physical knowledge and rigorous data analysis. When we do that, we obtain results that are really better, with sometimes often less parameters. So this is something which is really important. The physical knowledge of the physicist is really structuring for the solution that we can develop in the deep learning community. So we have the paper, the GitHub containing the code, and in this case, this package is available on the PyP, so it's easy to install through pip. So have a try if you want, and don't hesitate to ask us if you have any questions.
I don't have questions either.
I have one. So the original code based on physical model sometimes lead to anomalies. Okay. Have you experienced situations where your emulated code sometimes would lead to hallucinations or?
Hallucination? I don't think so. I think because you can have this information. The 99th percentile error is not that high, which means that there are not important hallucinations. In general, what can happen is that if there is an anomaly that has not been detected in the data set, the neural networks will sometimes get rid of it, but we have not detected any hallucination, as you said. It can happen if the network is not big enough, or if the network is too big, but in our case, it doesn't happen.
I saw in the news a paper about a very similar approach, or from a philosophical point of view, to approximate meteorological models. Those models are gigantic. It's kind of the same situation. You cannot change anything anymore because it's so complex. And they have approximated those models with deep learning. And it works. It was shown that it works better than the models for Météo France in average, but sometimes you would get hallucination like, oh, today it's going to be 30 grades in Grenoble.
Well, we have not seen this kind of behavior. It's not impossible, but according to the metrics, I don't think that it happens. It can happen if you try some very specific, maybe physical regimes that are not supposed to happen in reality and that were rare in the data. If you have something which wasn't present in the data because it was just in a region of the grid where there was no point, it's not impossible, but we have not seen that.
But overall, we tend to think that there is no such hallucination because the propositions that we made the 5 strategies that are highlighted down there have a regularization effects overall. So we don't tend to think that they're
Very safe.
yeah.
I think so, at least.